It's really great working in the lab. The temperature is comfortable for you and your circuits. You've got a nice, reliable power supply, and you've got your little wrist grounding strap, and you've got a scope to see exactly what's going on. Life is good. And then you send your creation into the real world, and things get tough. There's lightning and static charge and voltage spikes and heat and cold and salt water and ground potential differences. I mean, sheesh, if you can't even count on your ground, you should have designed in some isolation. Hi, I'm Amelia Dalton, host of Chalk Talk. Making a circuit that will work outside the lab in the harsh environment of the real world requires some isolation. Today, my guest is Neel Seshan from Texas Instruments, and we're going to dive into some really cool components that make that isolation issue a whole lot easier. And before we get started, don't forget to click that link. There you can find more information about isolation products from Texas Instruments. Hi, Neel. Thank you so much for joining me.
Thank you, Amelia, for having me.
Okay, so let's start off slow. What exactly is isolation?
Isolation is a way of preventing DC, an unwanted AC signal, from going from one side of the circuit to the other side of the circuit, while enabling data and power transfer between those two circuits. Isolation is used for a lot of reasons. If you want to protect and safely withstand high voltage surges that happen on the high voltage side and which could damage some equipment, then you want to avoid that. In some cases, like medical applications, there would be instances where the high voltage could be transferred from the high voltage board to a patient, and you do not want that to happen also. The other reason is there could be ground loops that would be present between these two circuits, and you want to break that ground loop. That would be another reason for using isolation. And lastly, you would use isolation where you want the high voltage side components and the low voltage side components to communicate effectively. So these are some of the reasons why isolation is being used. And on the right side, you see the image where you see the real world. It has all the data measurements like temperature measurement, speed measurement. All these are done. The transfer of data happens with transceivers, or it can happen with ADC circuits. And the communication on the other side to the PLC or the DSP is happening through this isolation layer. So in this case, you have the real-world analog signals being transferred from one side of the board to the other side of the board, which is doing the digital signal processing across an isolation barrier.
Okay, so can you elaborate on this ground loop thing?
Absolutely. So here you see an example of two circuits, and you have the left side circuit which has voltage supply 1 and the right side circuit which is connected to the supply 2. And there is two different ground planes. There is a ground 1 on the left side and a ground 2 on the right side. Now both these grounds may not be at the same potential. There could be some potential difference that happens between these two grounds. So on one side, if you have 0 volts and on the other side you have 1 volt, then you would say that the ground potential difference between those two grounds is 1 volt. Now what happens if you just short the two grounds? And in that case, a ground loop gets formed. And if you remember the simple Ohm's law, V is equal to IR or I is equal to V by R, depending on the resistance of that wire that you use to connect between those two grounds, now there could be a ground loop current that flows because you have a 1 volt potential that's applied. This ground loop noise or ground loop current is unwanted in these circuitry. This causes interference with the signal, and that would deter the data output, or the integrity of the signal could be harmed by this ground loop current. How do you solve this problem? Simply insert an isolator. Now what this isolator does is that it prevents the ground loop from being formed, so there is no current flow happening between the two sides through the ground loop. The voltage is still present, so the isolator needs to withstand this voltage that exists between the ground 1 and ground 2. So the isolator now has done two things. First thing, it has cut the ground loop, and the second thing, it's trying to withstand the high voltage that appears between the left side and the right side, or the ground 1 and the ground 2.
So where exactly would I use isolation?
Isolation can be used in a wide variety of applications, both in the industrial and the automotive domain, and even telecom and enterprise switching. Mainly in the industrial domain, you see the use of this in factory automation. PLC systems where they have 24-volt input signals coming in, and all these digital input signals are communicating with a microcontroller. And there you need isolation because the microcontroller is operating from a 5-volt or a 3-volt supply, whereas the sensors are operating from 24-volt supply. Isolated power supplies, that's another example. Test and measurement, grid infrastructure. In grid infrastructure, here you can think of where the electricity generation happens. You have the highest voltages coming from one side, but the control circuitry or the electronics may be operating again from 5 volts or 3.3 volts. So you have a big potential difference between the two sides, which makes it, a perfect place for isolation to be used. Motor control, again, you have high voltage motors, which are being driven by low voltage microcontroller circuitry. That's another example of isolation usage. And recently, if you look at the automotive trend, there is a surge of the demand for going green and all the electric vehicles that are coming up. So as this trend continues, the electronics content in these cars is also going to increase. And with that, we have 12-volt batteries, which will be replaced by 24 volts and 48 volts, all the way up to 690 volts. So in that case, you will also have isolation that will be used between these two sides. So applications such as battery management system, onboard chargers, traction inverter would be some of the examples where you would see need for isolation.
So where does isolated power come into the picture?
Oh, that's a good question. When you look at isolation is the transfer of data between the two sides. If you look at the image here, what happens is you're isolating the left side and the right side, but we didn't talk about VCC1 and VCC2. These are the two power supplies on the two sides. You cannot just simply short them because shorting them, all the advantages of isolation are lost. So what do? You take the VCC1 and you tie it to a DC-DC converter, or you drive a DC-DC converter, which then drives a transformer. That transformer now acts as isolation for power. And then you have rectifying diodes and an LDO, and the rectified output, VCC2, can now be tied to the VCC2 of the digital isolator. So this here shows a simple discrete implementation of the digital isolator along with the isolated power. This is one of the ways in which you get isolated power. Traditionally, there have been flyback, flybuck, or push-pull topologies that have been used, but the disadvantage of that is that they add extra space because of all these components that need to be added along with the digital isolator, and also there is a cost implication to the design.
Okay, so what solutions does Texas Instruments have?
I'm going to talk about a couple of solutions that we have. Two of these devices, the SN6505 family, and the next one which I'll talk about is the 6501. These two are low noise transformer drivers. Basically, they are available in very tiny SOT23 package, about 3 millimeter by 3 millimeter dimension. And what these do is that they take the supply voltage, which would be 2.25 volts on the input side, and they drive an external transformer. Now, with this external transformer, rectifying diodes, and a regulator, you are able to get a isolated power that can drive the VCC2 of your digital isolator. This device here, this family 6505A and B, provide 1 amp output current, and the only difference between these two devices with the A and the B flavor is the difference in the switching frequency, which is either 150 kilohertz or 400 kilohertz. The other advantage of the 6505 is that this has an enable signal. So if you want to shut off this whole power, the enable signal can be used to turn on and turn off this isolated power chain.
Now, what if I want low current?
Absolutely. So the 6505, this, as I mentioned, gives you 1 amp of current. This next device, the 6501, is a simpler device. It doesn't have the 6 pins. It doesn't have the enable pin or the soft start, which the 6505 has. But this device does the same function. It takes 5 volts or 3.3 volts at the input and provides around 350 milliamps at 5 volts and 150 milliamps at 3.3 volts. That is used to drive the transformer. And then you can have a rectifier regulator, just like in the previous case. It comes in the same package, just that it has 1 pin less as compared to the 6505.
Okay, so what if I don't want to add components? You talked about adding cost, etc., but can we avoid all of that?
Yes, there are ways in which you can have an integrated solution. And by that, if you look at the image on the left side here, this shows the traditional architecture where you have a digital isolator along with the DC-DC converter, transformer, rectifier, regulator. All the components in this dotted box can be replaced by a single component. And that's the integrated solution which would take the digital isolation channels and the digital isolated power and pack it into a single package. What are the advantages of this device? If you have them in a single package, then you're reducing the bill of materials, the board space drastically reduces. And with board space, let me explain that it does not just reduce it in the X and Y dimension, but transformers are known to have a certain thickness, which is more than what you can get with some of these integrated devices. So in the X, Y, and Z dimension, in all three dimensions, you're able to come up with a smaller, compact solution. Why is this useful? If you're looking at PLC systems, and in PLC systems, say you're going to stack a bunch of these boards, now you can make them even more compact because you're not limited by the height of those transformers. The second advantage of having an integrated solution is the system certification. What I mean by that, typically when these devices are going into, say, a medical application, then our customers will ask us, do you have certifications from UL, VDE, CSA agencies? Now, when you have an integrated device, you just need one certificate, whereas if you had discrete components, it's the designer who needs to ensure that all the components on the board are certified to that standard. So here, just one component, and all TI's isolators are certified by the UL, VDE, CSA, and TUE certification agencies. The information is available on the website, so ti.com. You should be able to find the certificates from these agencies. And lastly, it helps the reliability of these boards. When you have lesser number of components, especially when you're looking at isolation circuits, it makes it more simpler. And also, when you're looking at the emissions performance, the efficiency, you get much better performance with this integrated circuits.
Okay, Neel, can we get into a little more detail?
Let me talk about the ISOW78xx device. This family is a family of digital isolators with integrated DC-DC converter. It's available in both 2 channels and 4 channels. This device is capable of providing 130 milliamps at the output from either a 5 volt or a 3.3 volts on the secondary side. And if you select 3.3 volts on the secondary side, it can provide up to 70 milliamps load current. And it comes with an integrated DC-DC converter. So as I mentioned, you just have to provide the VCC1 on the primary side, and the secondary side gets generated inside this chip, so you do not need any of those external components. This does have a speed of 100 megabits per second, so you could be using it for a wide array of applications. The propagation delay typically is about 13 nanoseconds, and the EMI performance of this meets the IEC 61000 standard, so it's a very robust device with 8 kV HPM. And for customers who are interested in reinforced isolation, this device does meet the VDE reinforced isolation spec also. So it's a very powerful device in a 16 DW package, and as I mentioned, available in 2-channel and 4-channel.
All right, so how do I know what's right for my design?
So even within the 4-channel devices, we do have different flavors. So if you're using a SPI interface, you would want 3 channels in one direction, 1 in the opposite direction. So you need to make sure that you're picking the device which has the right number of forward channels and the right number of reverse channels. To make it easier for designers to choose, we have a variety of devices. We have all the way from 4.0 to 4.4, which gives you all the combinations. And then in a 2-channel, we have 1 forward channel, 1 reverse channel, which is typically what is used with the transceivers and receivers circuitry, where there's 1 transmit channel and 1 receive channel. All these are in the same package, so it's the 16 DW. And we also have fail-safe high and fail-safe low. So a fail-safe low is indicated by a F in the name. And what this does is that if there is any fault on the primary side, say your VCC1 got disconnected, or your input got disconnected on the primary side, the output side will transition to a low state. The fail-safe high orderable, if you choose that one, in case of a failure on the primary side, the secondary side will default to a high state. So again, depending on your application, you have an option to choose a fail-safe low, fail-safe high, or different channel counts.
Okay, cool. Are there other solutions in the market, and how does this stack up?
Absolutely. There is multiple solutions available, both in the discrete world and the integrated world. What I will show is the comparison with other integrated solutions that are available in the market. So here the blue and the green line represent a competitive device that's available in the market. The 2 lines represent the 2 supply voltages, one at 5 volts and one at 3.3 volts. And the output is programmable, but in this case, we've used a 5 volt input, 5 volt output, and 3.3 volt input, 3.3 volt output. If you compare the green and blue lines against this TI device, ISOW78xx, you can see that with the red line and the orange line, you get up to 50% efficiency. So 80% higher efficiency is achieved by this device as compared to another device which is available in the market.
All right, Neel, what about heat and efficiency?
Heat and efficiency go hand in hand. And here is an example where we see the TI device mounted on this board, and on the same board you have the competitive device. And on the right side, this shows the temperature profile of these boards in full operation condition. Here we have 400 milliwatt load, and the load is same for both these devices. And you can see that the competitive device is running at 90 degrees C, whereas the TI device is running at 50 degrees C. So about a 40 degree cooler operation with the TI device as compared to another device. Where this comes in handy is again a PLC application. If you have multiple boards that are being used at the same time, you want to worry about how much temperature is going to rise from these multiple channels being used. With the TI solution, now you can be ensured that you're going to run as cool as possible with these integrated devices.
Okay, so are there any other important considerations I should be thinking about?
Yes. Emissions is one important consideration. When you have a discrete solution, since the transformer and the driver are outside the chip, you can increase the size of the transformer. When you increase the size of the transformer, the switching frequency of that driver can be reduced. Since the switching frequency is low, emissions are going to be low for a discrete solution. But when you take that transformer, the driver circuitry, and put it inside this integrated chip, you cannot have a big transformer. So you end up reducing the size of the transformer so it can fit in the chip. And when you reduce the size of the transformer, the frequency of the switching driver has to be increased. And with that, the emission also increases. So typically, you're going to see higher emissions with the integrated solutions as compared to discrete solutions. But there are ways in which you can actually improve the performance. We have done some improvements within the chip, within the architecture of this device to keep these emissions as low as possible.
Okay, let's talk about emission performance. What's the story here?
So again, we've used the same board as I showed earlier for the temperature measurements, and this comparison compares a competitive device, which is in the blue color, versus the TI device in the red color. And the green line here is a standard, it's a CISPR 22 Class B line. Most of the customers typically use the CISPR 22 standard as a measure of how good your emissions performance is. And as you can see from this chart, there is about a 10 dB improvement in the performance with the TI's ISOW78xx as compared to the competition. So we do pass the CISPR 22 standard, whereas the competitive device is exceeding the CISPR 22 standard.
Okay, so if the power supply is provided by this chip, do we need to worry about startup?
No, actually, that's another feature of this device. If you compare on this chart, the yellow line here is the input power supply, the VCC1, to the competitive device. And the blue line represents the competitive device's isolated voltage on the secondary side. And you can see that there is a bump here, or there is an overshooting that's happening in this portion, which means there is no soft start incorporated in this chip. On contrast, if you look at the ISOW7841 curve, the purple line here shows the VCC curve versus the green line, which is showing the VISO, or the isolated. And there is a very gradual and smooth start to how this device powers up. So that's the advantage with this device, is that it has soft start included within the chip. So the designers do not need to worry about how the startup performance is going to be. And there's not going to be any high inrush current because of the soft start that has been implemented in this chip.
Okay, Neel, how would I test out this device?
We do have an EVM. The ISOW7841 EVM is available on the TI.com. This is a very simple EVM. You just connect the inputs and the VCC on one side, and you should be able to get the outputs on the secondary side along with the VCC2. And that VCC2 can be used not just for powering up other isolators, but any other circuitry that's on the board. This device is also capable of providing 650 milliwatts of power, which is 130 milliamps of current. So whatever circuits you have on the secondary side, as long as the current doesn't exceed 130 milliamps, this device will be able to power that up.
So, do you have any reference designs I could take a look at?
Yeah, we do have many reference designs on this device. I'm going to share with you two of these designs. The first one is isolated RS485 with integrated signal and power. We have seen that RS485 and RS232 are some of the most commonly used interfaces. So here is a board, and you can see how tiny this reference design board is. It has the ISOW78xx device on one side, and to keep this board as small as possible, we have put the RS485 device on the back side of this board. So it's a very compact design, and since this is low speed, you can have through holes from the ISOW device to the RS485 device on the backside. We do have test data for it. If you check out the TIDA00892 tools folder on TI.com, you'll be able to get all the plots and the test data for this TI design. On the same lines, we also have an isolated RS232 design, and the only difference here is that instead of using the RS485 chip on the backside of the board, we have used an RS232 device. Same thing can be implemented with isolated power and signal with CAN. So change the transceiver, use the same ISOW78xx device, and then you have a very compact solution.
Okay, cool. So Neel, can you give me a summary of what we talked about today?
Yeah, so to summarize, it's not enough just to isolate the signals. You need to isolate the power as well. And there are different options. For some customers, the discrete solutions may be preferable. In that case, we went over the SN65OX family. We have two different current levels. If you want low current, you have the SN6501. If you want higher current levels, then you can check out the SN6505. And if you prefer the integrated solutions where both the isolated data and power are in a single chip, then you have the ISOW784X family or the ISOW7821.
Excellent. Well, I think that's all I have time for. Thank you so much for joining me, Neel.
Oh, thank you very much for having me.
And before we go, you didn't forget to click that link, did you? There you can find more information about Texas Instruments isolation products. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal or check out YouTube. Keyword EE Journal.